The first question is calculate the wavelength separation between the two component lines which are observed in the normal Zeeman effect. The magnetic field used is 0.4 Weber per meter square. The specific charge is equal to 1.76 into 10 raised to 11 coulomb per kilogram and lambda is equal to 6000 angstrom. In the present problem, we have to determine the wavelength separation between two component lines in normal Zeeman effect. From the figure, lambda represents the unmodified line and lambda dash minus lambda double dash which represent the wavelength separation between the two components, which is actually 2 times the Zeeman shift in wavelength delta lambda, that is equal to 2 times the Zeeman shift in wavelength is E by 4 pi mc b lambda square. Now we can write it as 2 times b lambda square divided by 2 times b lambda square divided by 4 pi c into E by m. In the present problem, the specific charge is given. Specific charge is nothing but E by m and the value of E by m is 1.76 into 10 raised to 11 coulomb per kilogram. Also, the magnetic field used is 0.4 Weber per meter square. B is equal to 0.4 Weber per meter square and the wavelength used is 6000 angstrom, that is 6000 into 10 raised to minus 10 meter. Now substitute all these values so that we will get the wavelength separation between the components, that is equal to 2 into 0.4 into 6000 into 10 raised to minus 10 square divided by 4 pi times 3 into 10 raised to 8 into E by m, that is 1.76 into 10 raised to 11. The answer is 13.45 into 10 raised to minus 12 meter. That is the wavelength separation between the components lambda dash minus lambda double dash is equal to 0.135 angstrom. The next question is calculate the energy in electron volt of a beam of electrons used to excite hydrogen atoms so as to emit first Balmer series. In the present problem, we have to calculate the energy of a beam of electron required to excite hydrogen atom to emit the first line in Balmer series. The first line in Balmer series happens whenever there is a transition from Ni is equal to 3 to Nf is equal to 2 and this line is called H alpha line. We have the equation for wave number nu bar which is equal to 1 by lambda which is equal to R infinity into 1 by Nf square minus 1 by Ni square, and for H alpha line Nf is equal to 2, Ni is equal to 3. Therefore 1 by lambda is equal to R infinity into 1 by 2 square minus 1 by 3 square. This implies that 1 by lambda is equal to R infinity into 5 by 36. 1 by lambda is equal to R infinity into 5 by 36. Therefore, the wavelength lambda is 36 by 5 into 1 by R infinity. Lambda is 36 by 5 into 1 by R infinity. We have 1 by R infinity, that is 1 by Rydberg constant, which is approximately equal to 911 angstrom. Therefore, lambda is equal to 36 by 5 into 911 angstrom. That is equal to 6559.2 angstrom. That is lambda is equal to 655.9 nanometer. Lambda is equal to 655.9 nanometer. Now energy in electron volt, which is equal to 1242 divided by lambda in nanometer. Energy in electron volt is equal to 1242 by lambda in nanometer. Therefore, E is equal to 1242 divided by 655.9. Now the answer will be in electron volt. That is, energy E is equal to 1.894 electron volt. The next question is, an electron in a particular state of hydrogen atom has a magnetic potential energy of about 10 raised to minus 23 joule. Estimate the magnitude of magnetic field acting on the spin magnetic moment of the electron, which is of the order of 1 Bohr magneton. In the present problem, magnetic potential energy is given. The magnetic potential energy can be represented as minus mu s dot B0. That is, the magnetic potential energy is due to the interaction of the spin magnetic moment of the electron and the magnetic field produced due to the orbital motion of the electron. So, the magnetic potential energy is actually due to the spin orbit interaction. You can write it as minus mu s dot B0. Now take the dot product. This become minus mu s B0 cos theta. From the diagram, we can see that mu s cos theta is nothing but the z component of the spin magnetic moment of the electron mu s. So you can write it as mu s z. Therefore, the magnetic potential energy become minus mu s z B0. Let it be our equation number 1. We have the expression for mu s as minus gs e by 2m into s with the gs is equal to 2, where gs is the g factor for electron. Therefore, mu s become minus e by m into s. Therefore, we can write mu s z, that is equal to minus e by m into s z. We know that ms quantizes the z component of the spin vector. Therefore, sz can be written as ms h cross with ms is equal to plus or minus half. Now, what is mu sz then? It is minus e by m into ms h cross. Ms can have plus half or minus half. Now, in the case of hydrogen atom, there is only one electron. So, for convenience, take ms is equal to plus half. Now, mu sz become minus eh cross divided by 2m. If you take ms is equal to plus half, mu sz become minus eh cross by 2m. Now, eh cross by 2m is nothing but the Bohr magneton. Therefore, we can say mu sz is equal to minus mu b. Let it be our equation number 2. Now, substitute 2 in 1. You will get the magnetic potential energy E is equal to minus and minus cancel. E is equal to mu b B0. This is the expression for the magnetic potential energy, that is equal to mu b B0, where mu b is the Bohr magneton. We have to find out the magnitude of the magnetic field B0. Now, B0 is nothing but E by mu b. E is given in the question as 10 raised to minus 23 joule. Therefore, we can write B0, that is equal to E by mu b, that is equal to 10 raised to minus 23 divided by 9.274 into 10 raised to minus 24. And the answer is B0 is equal to 1.078 Tesla. The next question is, the moment of inertia of the CO molecule is 1.46 into 10 raised to minus 46 kilogram per meter square. Calculate the energy in electron volt and the angular velocity in the lowest rotational energy levels of the CO molecule. In the present problem, we have to determine the energy in electron volt and angular velocity in the lowest rotational energy level. We have the rotational energy levels allowed to the rigid diatomic molecule EJ is equal to h square divided by 8 pi square I into j plus 1 joules. Where the value of the rotational quantum number varies from 0, 1, 2, 3, etc. Now for the lowest rotational state, for the lowest rotational energy level, the value of J is 0. Therefore, EJ become E0, that is equal to h square divided by 8 pi square I into 0 plus 1 joule. That is, the lowest rotational energy E0 is equal to 0 joule. Therefore, we can say the lowest rotational energy E0 is equal to 0 electron volt also. Now we have EJ, that is equal to half I omega square. Therefore, the angular velocity omega is 2 EJ by I. For the lowest rotational energy level, the value of E is 0. Therefore, omega is equal to 2 into 0 by the moment of inertia is given 1.46 into 10 raised to minus 46. Therefore, we can say that the angular velocity in the lowest rotational energy level is 0 radian per second. The next question is given that the spacing between the vibrational levels of a CO molecule is 8.45 into 10 raised to minus 2 electron volt and the reduced mass is 1.14 into 10 raised to minus 24 kilogram. Calculate the value of the force constant K of the bond in a CO molecule. In the present case, the spacing between the vibrational levels is given. From that data, we can calculate the vibrational frequency of the molecule omega oscillation, and omega oscillation is equal to 1 by 2 pi into root of K by mu. From that, we can determine the force constant K. First, omega oscillation is equal to delta E by H. Delta E is given in the problem as 8.45 into 10 raised to minus 2 electron volt. Multiply it with 1.6 into 10 raised to minus 19 so that delta E is in joule. Now divide it by Planck constant. We will get the value of omega oscillation as 2.040 into 10 raised to 13 hertz. Once we have the vibrational frequency of the molecule and the reduced mass, we can determine the force constant K. It is given that the reduced mass of CO is 1.14 into 10 raised to minus 26 kilogram. Therefore, the force constant K is 4 pi square mu omega oscillation square, and that is equal to 4 pi square into 1.14 into 10 raised to minus 26 into 2.040 into 10 raised to 13 hertz square. That is K is equal to 187.3 Newton per meter. The next question is the wavelength of the exciting line in Raman scattering is 5460 angstrom and Stokes line is observed at 5520 angstrom. Find the wavelength of anti-Stokes line. In the present problem, the wavelength of the exciting line is given. The wavelength of the Stokes line is also given. From this data, we have to find out the wavelength of anti-Stokes line. Let nu 0 bar be the wave number corresponding to the Rayleigh line. Let lambda 0 be the corresponding wavelength. This is the same as the wavelength of the exciting line. Let nu s bar be the wave number corresponding to the Stokes line and the corresponding wavelength be lambda s, and let nu a bar be the wave number of anti-Stokes line and the corresponding wavelength be lambda a. Now the Raman shift in wave number is given by nu 0 bar minus nu s bar, and the wave number of anti-Stokes line is given by nu 0 bar plus this Raman shift in wave number. Now what is the wavelength of anti-Stokes line? It is 1 by nu a bar. In the present problem, it is given that the wavelength of the exciting line is 5460 angstrom. So we can say that lambda 0, which is the wavelength of the Rayleigh line, which is also 5460 angstrom. That is 5460 into 10 raised to minus 8 centimeter. Now the wave number corresponding to the Rayleigh line is 1 by 5460 into 10 raised to minus 8 centimeter, and that is 18315.02 centimeter inverse. Now let us find out the wave number corresponding to the Stokes line. It is given that the wavelength of the Stokes line is 5520 angstrom. That is 5520 into 10 raised to minus 8 centimeter. Now the wave number corresponding to the Stokes line is nu s bar, that is 1 by lambda s, that is 1 by 5520 into 10 raised to minus 8, that is 18115.94 centimeter inverse. This is the wave number corresponding to the Stokes line. Now we can find out the Raman shift in wave number delta nu bar as nu 0 bar minus nu s bar. This is the Raman shift in wave number, and this is equal to 18315.02 minus 18115.94. That is the Raman shift in wave number is given by 199.08 centimeter inverse. Once we have nu 0 bar and delta nu bar, we can calculate the wave number corresponding to the anti-Stokes line as nu a bar, that is equal to nu 0 bar plus delta nu bar, and that is equal to 18315.02 plus 199.08. That is the wave number corresponding to the anti-Stokes line is 18514.11 centimeter inverse. We have to find out the wavelength of anti-Stokes line. So take the reciprocal of nu a bar, that is lambda a. The wavelength of anti-Stokes line is 1 by 18514.11, that is equal to 0.0000540129 centimeter. Therefore, we can say that the wavelength of anti-Stokes line is 5401.29 angstrom. The next question is, what is the minimum voltage to be applied to an X-ray tube to produce X-ray of 1 angstrom? We know that the minimum wavelength of X-ray which is produced from the X-ray tube is given by hc by Ev, where V is the accelerating potential. It can be simplified to lambda in nanometer, that is equal to 1242 by V. It is given that lambda is equal to 1 angstrom. Now that is equal to 0.1 nanometer. The expression for minimum voltage, that is equal to 1242 by lambda, where lambda is in nanometer. Therefore, we can say V is equal to 1242 by 0.1, that is 12420 volt, or V is equal to 12.42 kilovolt. The next question is, calculate the wavelength separation between the unmodified line of wavelength 6000 angstrom and the modified lines when a magnetic induction of 1 Weber per meter square is applied in normal Zeeman effect. In the present problem, we have to determine the Zeeman shift in wavelength. The Zeeman shift in wavelength is defined as the wavelength separation between the unmodified line and modified lines. The expression for the Zeeman shift in wavelength is given by delta lambda is equal to E by 4 pi mc b lambda square, and that is equal to 1.6 into 10 raised to minus 19 divided by 4 pi into 9.1 into 10 raised to minus 31 into 3 into 10 raised to 8 into b lambda square. On simplification, we will get the expression for the Zeeman shift in wavelength delta lambda as delta lambda is equal to 46.7 b lambda square. In the problem, it is given that the magnetic induction B is equal to 1 Weber per meter square and the wavelength of unmodified line is 6000 angstrom, that is 6000 into 10 raised to minus 10 meter. Therefore, delta lambda is equal to 46.7 into 1 into 6000 into 10 raised to minus 10 square. The answer will be in meter, and that is equal to 16.812 into 10 raised to minus 12 meter. That is delta lambda is equal to 0.168 angstrom. The next question is, calculate the strength of the magnetic field required to give processional frequency of 100 MHz for oxygen 17 nucleus, given Gn is equal to 0.757, mu n is equal to 5.051 into 10 raised to minus 27 joule per Tesla, and I is equal to 5 by 2. In this problem, we have to use the equation for NMR resonance condition. The equation is H nu is equal to Gn mu n B0, and from that equation we have to find out the strength of the magnetic field. From the NMR resonance condition equation, we can say that B0 is equal to H nu divided by Gn mu n, where Gn is the nuclear G factor and mu n is the nuclear magneton. It is given that nu is equal to 100 MHz, that is equal to 100 into 10 raised to 6 Hz. The nuclear G factor is given in the question as 0.757, and the value of the nuclear magneton is 5.051 into 10 raised to minus 27 joule per Tesla. Therefore, B0 is equal to 6.626 into 10 raised to minus 34 into 100 into 10 raised to 6 divided by 0.757 into 5.051 into 10 raised to minus 27. That is, the magnetic field B0 is equal to 17.33 Tesla.